Okay, so now this is where the videos can get a little more rational. Length, they're not going to be quite as long now because we're not doing all this graphing and explaining of stuff. So one of the things that we need to sort of discuss is that this exponential growth is actually kind of useful, right? It really is. It's kind of useful. And it helps us with things when we're talking about like percentage rates and any kind of that stuff. And the biggest thing it helps us with is it helps us with growth, with when we're talking about population growth, right? Because population growth is exponential because as you start getting more and more people on, that means more and more people are able to also have their own babies, right? And they have babies, and then eventually their babies have babies, right? And so it's kind of like rabbits, right? Except in this case, we're talking about, kind of normal people. But in order for this to happen, right, we got to have something to kind of work with. And so we have this formula that we're going to work with. And this is based off of kind of our y equals, bx, b to the x, or 2 to the x, y equals b to the x model, right? It's based off of this, right? Except that now what we're doing is the thing that we're raising, we're going to add something to it. Later we're going to subtract something to it, and then we're also going to have this transformation where it opens up either fast or slow depending upon what a is, right? And so this is basically, the way you can remember this and differentiate this from the other one is this is growth, and this is the one where you're adding, right? So we can use this, all right, t stands for, so your variable in this one, right? We're not using x in any of these, right? We're using t for time. And so t is basically our x, but t stands for time periods, right? A is the initial amount you're going to start with, and r is the percent of increase per time period. And so we'll kind of go through one of these and see this. And then, so the thing that is being raised to the exponent is your growth factor, right? So that's the thing that really makes the difference of what's happening here, right? And then, like I said, these are used for population growth. So let's take a look at this. All right. So this one says the first U.S. census was conducted in 1790. At that time, the population was 3,929,214. Right. So basically a little bigger than the city of Chicago. Right. Since then, the U.S. population has grown by approximately 2.03% annually. Draw a graph showing the population growth of the United States since 1790. And so let's basically, let's think about this, right? And so we're not really interested in drawing a graph. What I want to say is let's pose a different problem, and this is more similar to what you're going to have to actually do with this, is you're going to say using this, right, using this model, all right, predict what the U.S. population was in, so we'll say in 1990, all right? So we got 1790 to 1990, so 200 years, right? And so let's see if we can do this, if it's going to give us insanely large numbers or what we can do. But so the way we set this up, right, is our A of t, right, is equal to, my A is my initial amount. So my initial amount, you're going to use this number right here. So we're going to go 3,929 times 214. Now we're going to go 1 plus my R. My R is 2.03%. So we got to write this as a decimal. So it's going to be 0.0203, all right? And while it might seem trivial to include this, it's really important, okay? And then we're going to raise this for my t, and my time period is 200 years because you're going from 1790 to 1990. So to the 200 power, right? And so this simple formula, believe it or not, is going to tell us what that is, right? And so here's what I do, okay? And so now I gotta get a slightly more powerful calculator here. So I'm going to get my calculator off my phone working here if it ever decides to let me open it up. Okay, so let's pull that up. Okay, so I'm going to go, I'm going to use my y to the x function, or x to y function that you can do with your phones, right? So I go x, so my x is 1.0203, and I'm going to raise that to the 200 power. And that gives me this 55.6643 like number. It's not as big as you think it's going to be, but it's still plenty big. And now I'm going to multiply that by 3929214 by that 3 million number. And then I get, as a result, I get 218,717,238 point something, but it doesn't matter because you can't have percentages of people. And so let's look this up really quick, and let's say population of U.S. in 1990. All right, and the population of U.S. in 1990 was 250.1 million, right? And so is it completely accurate? No. But all things considered, is it relatively close? Yeah, it's within 30 million. That's pretty close. And you got to remember that too, that the population grows at different rates at different times. So these are kind of really cool models. What you can do with these, right? And you can get pretty close. When you're talking about 218 and you're only off by 30, that's it's not that huge of a percent off. All right, so let's try another one, and these are the ones that are really, really interesting, right? A virus spreads to a network of computers such that each minute, all right, that's important, 25% more computers are infected. If the virus began at only one computer, so that only one computer is going to be our initial amount. All right, that's our initial amount. Graph the function for the first hour of the spread of the virus. All right, so first hour. Well, if we're talking about minutes, that means 60 minutes. All right, so that's going to be my t, right? So when we write this, when we write a of t equals my initial amount, all right, so I'm going to just write this out, so 1 plus r to the t, right? So my a is 1, right? That's my initial amount, one computer, times 1 plus r, so we have 1 plus 0.25, so this is going to be much bigger, right? And then t to the 60, and so if we simplify this, we can drop the 1, and we're going to have 1.25 to the 60th power, right? And so let's bust out, right? Now remember, the virus began in one computer, right? So let's see, if a virus starts in one computer and is growing truly that quickly, how many computers, make a prediction, how many computers do you think are affected? Do you think it's going to be like 100? Or what do you think it's going to be? And the number is, and this is nuts, the number is 652,530.4 blah, 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 blah computers, right? So this many computers, right? Almost, between 600,000 and 700,000 computers are affected within 1 hour, right? With this crazy serious virus. So these, like I said, these exponential growth things are fun to play with and are seriously interesting, right? So there you go. All right. Next, we'll start talking about exponential decay, and then that's basically kind of the opposite of where we've been. All right. So thanks for your patience with this and for following along.